you very much. So it's my great pleasure to attend this conference and give a talk. So first, first day, Sasha. So I visited Loughborough 15 years ago when we both are very younger. This is Sasha's photo. So he was so kind. Um, then so we had 2 weekends, and he brought me to make some nice sightseeing. So it was a very nice memory for me. So I hope you continue very active life, please. Yeah, yeah. So right. So this talk is based on a joint work with Atsuo Kuniba, Yuji Terashima, and Junya Yagi. And so this preprint appeared this morning. So very, very new one. So please visit this site if you're interested in my talk. So first, I recall a notion of six vertex model and the very famous one first. So let V be the two-dimensional space with VO and V1, and I write Lx for the Boltzmann weight. This. So in state are I and J, and outgoing states are A and B, and we are allowed to have non-zero Boltzmann weight for these six configurations. I don't write the Boltzmann weight exactly, but they depend on the spectral parameter X. And so to get the integrability for this system, we define the monodromy matrix. So it's like this. And the Yang-Baxter equation is the most important thing, as you know. So this is RLL is LLR and depicted as this. So say LX lives here, LY lives here, and we have R here. And by moving this R from right to the left like this, and these two vertices are interchanged, and this gives a commuting transfer matrix by taking a trace of this monodromy matrix. So this is the essence of the integrability for the ordinary six vertex model. Then now I go to the quantized version, and it was introduced by these people. And we four parameters RSFG like today, and this model was introduced by Kuniba, Matsuike, Yoneyama recently. So again, we use this two-dimensional vector space, and additionally, we use QI algebra. And this algebra gives a non-commuting Boltzmann weight for this model. And so now this L, depending on four parameters, they are not spectral parameters, is in the endomorphism on B tensor V with coefficients corresponding to Boltzmann weight in the QY algebra. Then the model has the same appearance as the original six vertex model, but now you see that some Boltzmann weights are non-commuting variables now. Then we consider a two-dimensional lattice model by using these weights, like this square lattice, for example. And we want to have a family of commuting operators by taking a trace of this two-dimensional thing. So we consider a model on the torus for now. Then to get such a commutativity of layer transfer matrices, we use tetrahedron equation introduced by Zamorchikov in 1980. I think it is very famous one. It was introduced as the higher dimensional version of Yang-Baxter equation. And for this one, we use this picture. So different from the R operator for Yang-Baxter equation, it has three in states, IJK, and three outgoing states, ABC. And so by combining this R like this and this, we get some equality of Boltzmann weight for this tetrahedron equation. So we start with R456 assigned here, and 236 1, 3, 5, and 1, 2, 4 in the left-hand side. And in the right-hand side, the ordering is opposite. So now in this picture, these numbers from 1 to 6 denotes that don't denote the states, but it denotes the number of wires. So the how to say, it's number the states of tensor product. So from 1 to 6. So so this both sides acts on the tensor product of 6 vector spaces like this. Then the name tetrahedron came from the shape of the center. So we have tetrahedron and tetrahedron in the different, say, shape. Then, based on this equation, for the quantized 6-vertex model, we use these types of tetrahedron equation first. Then, now we assign this L. So this is the same as this one, but now I add blue arrows in the here to denote the space where QI algebra acts. Then with this picture, in this so in this case, we have 3L here, and this corresponds to this one. So L1 to L236, 135, 124. And we put this operator R acting on the product of 3 QI algebras R. And by moving this R from top to down, and the shape of black arrows are changed by this relation. So now we have opposite order of this. Then, if you look at these two pictures from the top, by ignoring these blue lines, then you see that this is a kind of higher dimensional Yang-Baxter relation. So in other words, the adjoint action of this operator R gives a Yang-Baxter map with respect to these black arrows. So actually, for the quantized 6-vertex model, we introduced this relation in our previous paper published in the last year. So this R is a very complicated one, constructed by using a quantum dialogism function based on the application of cluster algebra to this setting. But this is another story, so I don't go this on seriously today. Then, so to construct the commuting family of layer transfer matrices, we need a new tetrahedron relation, like so MLL relation. This is a new one written in our latest paper. So besides L, we introduced another operator M, like this. So we also have so QI algebra along acting on this green arrow, but a little bit different QI algebra we use. Then anyhow, so they satisfy this kind of relation, MMLL relation. So this picture is understood in the following way. By moving this green line associated to this operator M from north to east to southwest, then these two L are interchanged. So it means that 135 and T4, 245 are interchanged by moving green arrow from northeast to southwest. So then it means that if we define this kind of monodromy matrix, layer monodromy matrix, by moving this green arrow, so we put green arrow here, and we try to move it to go down and left, and so two layers may be interchanged. So this is what we expect. Then we can show the commutativity of layer transfer matrix. So the trace of this big operator. So to introduce spectral parameters x and y, we add some operators at the boundary of the fundamental domain of the torus later. Then we get some integrable, so commuting family of transfer matrices. Then first, I will start with square grid, as I shown. Then we try to generalize this underlying graph to be admissible. So it is a wiring diagram on the torus satisfying some condition called admissibility. So this is a story I will talk today. Then let's recall the quantized six-vertex model again. So we have a dimensional vector space and QR algebra satisfying this Q commuting relation. And so we have two operators, L and M. So L is already defined, and for M, we use another corpus of parameters with this prime. And so for part of QY algebra, we use W minus Q. It is obtained from this definition by replacing Q with minus Q for technical reason. Then we consider a square grid for the first time and to define some model. Then we already fix a fundamental domain on the torus. Then to introduce spectral parameters, we put these blue balls at the boundary, northeast boundary. And here, x and y are spectral parameter, and h is an operator defined in the following way. So h acting both v and qy algebra in this way. So for v, it counts a number of v1 at the boundary. So by this relation. And for QR algebra, it commutes with e to u, but it doesn't commute with to minus w and so on. And the first lemma is that if we consider operator L, 1, 2, 3, acting on the V tensor QR algebra, so we number these three spaces, 1, 2, 3. And so this means that HI acts on the ith space. So our claim is that this operator commutes with both L and M. So pictorially, it means that if we have this one, we attach some blue balls to arrows, and these balls can be moved safely to the opposite side. This is the meaning of this one. Then we use the following 4 tetrahedron relations. So the first one is the ordinary type. This is what I explained already. And second one is horizontally reverse type. So if you look at this picture seriously, you find that the direction of arrows of these 1 and 2 horizontal black arrows are reversed. So this is why we call this. And the third one is a vertically reverse type. So we now reverse the direction of black vertical arrows from this. And in the last one, we reverse both horizontal and vertical. Then for H and V, we need these conditions to operate the M. So this is a relation, a condition for the parameters for M. So this and this. For O and T, we don't need any condition. So please remark that this second conditions are different. So this is a point to introduce the notion admissibility later. Then, moreover, we use these two relations. So these may remind you of the unitarity condition for R operator for Yang-Baxter relation. So we have these relations. So so again, is to have some condition for parameters for M. So okay.
Sorry.
So yeah.
I'm a bit lost. So could you maybe remind a bit what's pictorial, what the pictures, which relations are encoded in pictures? Like what is M, L, R? Like
So for this picture,
maybe
this one.
was also here.
Okay, yeah, yes. Okay, so I omitted many things. So for this one, this ordinary one, we write MMLL is LLMM. So it's just to follow the direction of arrows. So first one is start with this one, and second one is this one. So it's just a so this order is how to say understood as the the number of incoming and outgoing arrows for each vertex. So it is all arrows are outgoing. So to say so 1, 2, 3, 4 is order. So in this way, you can draw you can write down the relation MMLL something by following the direction of arrows. So sometimes it is not well ordered, so we have to be careful to write down. And also this is for M times M, roughly. This. But please take care the direction of this arrow. So it is a little bit complicated. Is it okay? Thank you. So next, I'd like to construct commuting transfer matrices. So first, I start with square lattice on the torus, and we define a monodromy matrix in the following sense. So let G be an M times M square lattice like this on the torus. So we fix a fundamental domain like this now. And so monodromy matrix or layer monodromy matrix is the operator acting on V tensor M and V tensor N. And this is a space of M and multiplication of QY algebras. So each QY algebras live on the vertices. And if the vertices are different, they are commuting. Then this space lives here. So we have M in states and we have N in states. So in this direction and this direction. And by applying this T on this one, it means that this state, and it is changed to A and B, and its amplitude is given by a non-commutative variables. So this Tijab belongs to this space, the product of QI algebras. Then we add the information of spectral parameter here, and X to this A means the number of V1 on these states, and this B, absolute value of B means the number of V1 on these states, and so on. Then we take a trace of this monodromy matrix by make an equality of J1 equal B1, J2, and so on. And we get some operator in this space finally. And so, but in this definition, in this picture, I didn't put blue balls yet, but it will. And this one is called layer transfer matrix. And we want to show that these coefficients commuting. So first main theorem is this one. So this transfer matrices, it is a polynomial in X and Y with the coefficients in this space form a two-parameter commuting family. So namely, satisfy this commuting relation. Then, how to prove this? today I show the outline of loop by using only pictures, basically. Then, okay, so we
Formula.
so this is the one monoid matrix in front, and in back we have the copy of this, and we want to change this them from now by multiplying operator m at the boundary like this. So we set m plus n copies of m at northeast boundary like this, and we move this green arrow to southwest by using this one by one. Then in this case, because direction of all black arrows are unified, so how to say it, they are all the same. So we only use the ordinary type like this, and we move this green arrow gradually to this place. And so if you look at this picture, so if you project this picture to the plane vertical to this blue line, you find that this picture, simplified picture. So we just move. So these two vertices are identified in this picture, and you move this green arrow from how to say this place and go across this vertex, and we move this one. So I will use this picture to simplify the situation later. Then next, I put spectral parameters at the boundary of, so we had this equality, this one, due to tetrahedron equation, and we put these blue balls at the same place in both sides. And next, we move the blue balls in the left picture by using this relation. So now these balls are moved inside like this. But because of the existence of this part, we have several additional parts here. Then you see that in front on this layer, spectral parameter h and u, and in back layer, it has y and x. So here, rarely these two layers interchange. So in front, it has y and x, and in back, it has w and u. And in this way, we can really interchange. Then finally, we have more two steps. So we want to remove this additional part safely. So we change the previous picture to this one. And next, I take a trace of the green wires here. And now you see that these two pictures are the same, actually. And so mathematically, so it gives the invertible operator R. So from this picture, we get this relation. So TXY means layer modular matrix in back, and this TUW is a layer modular matrix in front with spectral parameters at the boundary, and this R denotes this green part. Then in the right-hand side, we had a similar structure, but the order is opposite. And here, this R is nothing but the quantum R for some UQ, so some quantum group. And so the good point for us to have this one is this R is invertible. So we multiply R inverse from the left, for example. Then by taking a trace in so this black arrows, and we get the commutativity of the trace of this monodromy.
I mean, would anything change if I chose the blue as opposed to the green line to do this?
This one. So to get the tetrahedron equation, we really need the difference between L and M. So actually, the difference was very small here. So just use this QI algebra for M. So we really need this for technical reason. So only this L, we don't get tetrahedron equation. This M we have. Yeah. Now, so we moved the commutativity of layer transfer matrices by using fixture for today. And so next, I want to generalize this strategy to deal with more general wiring diagram on the torus. Then, for that purpose, I introduced the notion of admissibility of the graph. So we had 4 tetrahedron equation and 2 inversion relations. Then we divide them into 3 groups. So type A, for type A, we have 3 one, B and I and inverse of I. So basically we go from left to the right. So this and these are treated as the inverse of each other. And so for this moves, we are required to have this condition for parameters of operator M with green arrows. Then type B is related to this condition. We have H and I prime and inverse of I prime. And the last group is more convenient. So ordinary one and total reversed one has no condition. So we divide these operations, these moves into 3 groups. And so it is obvious that we cannot have type A and B at the same time because these second conditions are different. So for generic Q. So the notion of admissibility is defined as follows. So let G, a directed graph on the torus, is exactly 2 wires meet at each crossing. So we assign this condition to define vertex model on this graph. And G is admissible if the initial northeast arrow, so as you see, northeast arrow can be moved to the final southwest arrow by applying the previous 8 move. Then, as I required, so, but we don't allow to have type A and B at the same time. So the condition of admissibility is that we can move green arrows from northeast to southwest, but type A and B do not coexist. So then we call this condition admissibility. Then this is an example of admissible graph. I will show that this is really admissible later. And if you reverse this middle arrows, then it becomes non-admissible one easily. So it is very naive definition. And to define layer transfer matrix, which includes spectral parameter, we define the following way. So when we deal with the square grid lattice, we add, so maybe this one, we add this blue ball in the same way. So because these black arrows are outgoing always in the square grid lattice. But now we have a little bit different situation. So some arrows going out, but some arrows are coming in. So if the arrow is going out, we put H to X to H, the horizontal one. And if arrow is coming, then we put H to X to minus H, sorry. And we do the same for the vertical arrows here, Y to H or Y to minus H. Then we can define the monodromy matrix for admissible graph G. And by taking a trace of that, we think that this main theorem. So if G is admissible, then we can move green arrows from top to down. So the corresponding transfer matrices are commutative. So I don't show the proof of this one for today, but the outline is the same. But because this footing are a little bit different, so we need some additional discussion. Next, so in this way, we can get the commuting family for a given admissible graph G. But the problem is that it is not easy to judge if a given graph is admissible or not. It is difficult. Yes.
This notion of admissibility is somehow natural. Why exactly 8 moves?
Sorry.
Why is this notion of admissibility is natural in any way? Why exactly 8 moves?
Yes. So we have eight moves, and
When you say 8 moves, you mean by using those 8 moves, not exactly 8 moves, is it?
not exactly. So do you mean that is there?
Only 8 moves allowed.
Only 8 moves are allowed.
Types of
Yeah.
move.
So
8 types of move.
8 types of move. 8 types of move.
actually, so we have no idea to find the other moves. So you see that. So maybe it is a maximum, I think, because so as for tetrahedron equation, so we have not many choices for the direction of arrows. So I think 4 is the maximum. And the notion of admissible came from the these different conditions. So
The number of moves is not 8, it's the types. Number of types, 8.
so number of moves
Two
so
times 4 is 8.
2 times 4.
No, it's 8.
Because you have 2 choices.
right.
Yeah.
And we have this including inverse.
With these, yeah.
Yeah. Yes. And okay, so yeah. Then so what I think so yes. So so we have the following conjecture to judge admissibility of given graph. So if G includes non-oriented face on the torus, then it is admissible. But unfortunately, it is conjecture still now. So we didn't succeed to prove that, but we can easily prove the reverse of this claim. Namely, if G includes at least one oriented face, then it is non-admissible. So it gives a judgment for non-admissible graph. So let's see an example. So this is an example of non-admissible one, and it has oriented face here, for example. So by following the direction of black arrow. So yeah, it is easy to prove this proposition, but conjecture is a little bit harder for us for now. But anyhow, can distinguish non-admissible graph.
So you can prove commutativity only for admissible. If they are not admissible, you have no any statement.
No. Then let's see an example of the admissible one, this one. So first we start with this picture. We put this green line at the northeast part. And we move this wire gradually. And we can move like this trivially. And we want to cross this vertex, for example. Then we use move H actually. So this H comes from the direction of black arrow. So we move this one to the opposite place, like this. And next we go across this vertex, for example. Then we apply H again. And now we have this crossing of green and black arrows. And to remove this, we use inversion relation like this. For example, I prime. And so at the same time, we can apply move O to go across this vertex and like this. And so next, we want to close this vertex, but for that, we need to move this green line in this way first, because of the rule of move. So in that's so here we need the inverse of I prime, for example. And after that, we apply all, and now every vertices are crossed. So we have the final stage. So in this way, we move green arrows from northeast to southwest. So I don't say that this move is unique. We have many, many choices. Then now we get commuting layer transfer matrices for admissible graph G. And so I'd like to mention the symmetry of these transfer matrices. So we have a freedom to choose the fundamental domain only. And first claim is that this transfer matrix is invariant under the translation of fundamental domain. It's, of course, it's very natural. And the second one is as well to the action on the fundamental domain like this. So it changed the fundamental domain, but essentially, so the transfer matrices are, how to say, changed nicely, and essentially they are not changed. So, so this is a symmetry of transfer matrices. And besides this, we have symmetry about the graph, which comes from a Yang-Baxter graph I introduced in the introduction by use RLL relation. So by the adjoint action of this R, so the graph G is locally changed. And due to this change, the monodromy matrix T is changed as this. So it is a kind of adjoint action of this R on the Q-wire algebra. Then, in particular, if G graph is admissible, and this admissibility is preserved by this action, it is easy to know this. So we have this Yang-Baxter move for given graph G. So in this way, we can construct some integral systems of 2+1 dimension by using tetrahedron equation. And so this is the end of my talk. So I give us a summary and some remarks. So we constructed some integral model on admissible graph. And so I'd like to mention that relation to quantum cluster algebra I said. So to construct RLL relation to give a symmetry of Yang-Baxter move to this model is related to quantum cluster algebra in the following way. So this is the red wires denotes the Yang-Baxter move of wiring diagram. And to this diagram, we can attach this quiver. So this quiver is what we call symmetric butterfly quiver. It has a very rich structure, actually. So this quiver is changed to this one by applying 4 mutations. Then, corresponding to this the operator, a joint operator to change the graph with Q-wire algebra is written as the combination of 4 quantum diagonal function plus something. So it is a very complicated operator, but by using quantum cluster algebra, we can construct that. There is another story with quantum cluster algebra to quantize 6 vertex model. And interestingly, our quantized 6 vertex model can be related to many interesting integral systems. So first example is relativistic quantum Toda chain. So if we consider this graph G on the torus, we can construct the commuting family, including Hamiltonian for relativistic quantum Toda chain by using Q-wire algebra. And we also have a relation with diamond model. So our quantized six-vertex model is equivalent to this diamond model with this non-commuting weight on the edge. And actually, and the clustering matrix for this diamond model and Lux matrix for this relativistic toda. In the classical case, this Lux matrix was written by Ruschi and Lagnisco, and so they are the same. But now everything is quantized. So we hope that there are other interesting relation with quantum or non-commuting integral system by applying this structure to various G. So this is the end of my talk. Thank you very much.
Any questions for Rei?
In the one dimension.